Yeah, welcome to our last talk in this session. We are delighted to have Mathew Young as our speaker. He will give a lecture series about moments of L functions.
Okay, great. So I was going to just use my tablet to write. Great, yeah. So so thanks to the organizers for letting me do this online. I had some medical problems with someone in my family, and so I couldn't attend. I really wanted to come to India. I've never been there. I'd love to visit. So just to start, I guess, so this is supposed to be about moments of L functions. I thought I would mention, so if you're looking for some kind of references, so the main reference for this will be, so there's the book by Iwaniec and Kowalski, Analytic Number Theory. There's the book by Titchmarsh. Okay, so probably by now everyone knows Iwaniec and Kowalski. Kowalski. There's a book by Ivich on the Riemann zeta function that has some things. There's a book by Motohashi on spectral theory of the Riemann zeta function, which has some things about moments in there. And then there's also okay, there's some multiplicity of the letter I. So then there's some books by Iwaniec. Okay, maybe I should call that IV then. On his automorphic forms books, or one on topics in classical automorphic forms, and then the spectral theory of automorphic forms. So a lot of what we'll be talking about will be drawn from these books. And so if you want more information, like more detailed proofs and much more information, then go there. So to start, I thought, okay, so I don't know what all what was discussed in the previous talks or previous sessions, and so there might be some repetition, and maybe that's okay. So so to begin, I wanted to give some just definitions and examples of L functions, and this will set up the notation that I like to use. So so this is more or less following the book of Iwaniec and Kowalski, which is really the only book that it was the first book that talked about the analytic theory of L functions in this way. So okay, so what's an L function? So an L function starts out as a Dirichlet series. So it has some kind of coefficients. I like to call them lambda f of n's. So it's a sum from 1 to infinity, lambda f of n over n to the s. And I want to assume that this converges for real part, let's say converges absolutely for real part of s bigger than 1. So f is some object, doesn't really have any real meaning, at least in the book of Iwaniec and Kowalski, but it's suggestive. It's supposed to suggest that there's some underlying object that's giving rise to this. And okay, maybe let's not say too much more about that right now. So we're going to assume that this has an infinite product, an Euler product. So it's an infinite product over primes. And then for each prime, it factors into the following shape. So it's 1 minus some number alpha I of p over p to the s inverse. And it's a product from 1 to d. And so here, and d is the degree. So d is a positive integer. Okay. And all right, so that's reflecting the multiplicativity of the lambda f of n's, and it's and it's just saying that we get this degree d type factor. I'll give some examples in a little bit, but let's first just set up all the notation. So we're going to assume that there's a gamma factor, which is going to again be a product from 1 to d. And then I like to use this notation gamma sub r, gamma the real numbers, of gamma of s plus kappa I, where here kappa I are some complex numbers. And so we'll have more information about that than just that they're pure complex numbers. But anyway, yeah, so there's some complex numbers. What's gamma r? So gamma r of s is pi to the minus s over 2. Sure, you can read this. Times gamma of s over 2. So it's also convenient to define gamma sub c. So this is kind of a parenthetical comment. So there's gamma c of s, which is defined to be 2 times 2 pi to the minus s, gamma of s. And then there's a relation between them. So gamma c of s is the same as, so using gamma function identities, you can prove that gamma c of s is gamma r of s times gamma r of s plus 1. So sometimes for some L functions, it's natural to have, like the gamma factors that sort of pop up naturally are gamma c's. And then you can always write a gamma c in terms of 2 gamma r's. Using this identity. So anyway, so sometimes we'll use this because it's a little bit convenient. Okay. So then, oh, and by the way, I think I can also share these slides that I'm writing. I think I can just save them as a PDF and share them with the participants. Okay. So then now, given the L function, there is a dual L function. Dual L function that we'll call L of f bar s. And so this will be a Dirichlet series where the coefficients are their conjugates. So you get lambda f of n complex conjugate over n to the s. And so that means that the alpha i's, so the alpha i's are conjugated. I don't know how to write this nicely, but this has an Euler product just like the original L function did, but just all the alphas are the conjugates of the original alphas for L of fs. So there's also a gamma factor for f bar. And this is a little bit more complicated to say what these are. So this will be a product from 1 to d again, gamma r of s plus, I don't know, kappa I prime or something like that. And conjecturally, the kappa I, so the set, the set of the, I mean, an individual kappa I is not really well defined, but the set is defined because you know which one's kappa 1 and which one's kappa 2 and so on. But the set of these sort of dual kappas should just be the same as the original one, but conjugated. But it's a little more complicated. So for example, so you could see I found theorem 6.5.15, and there's this book by Goldfeld. So Goldfeld's book, Automorphic Forms and L Functions for GLNR. So he works out. So I think I found the version for GL3, and so he writes down what the dual versions of the kappas are, and but yeah, it's slightly more complicated, but conjecturally it should be the same. So anyway, so there's some sort of dual object, and it has some well-defined parameters. Okay. another hypothesis is that there exists a positive integer q that we might call q of f. And then we put all these things together. So there's what we call the completed L function, capital lambda of fs. So this is defined to be your q to the s over 2, your gamma factor, and then times your L function. And so this has meromorphic continuation. To the whole complex plane. And the only possible poles, if there are any, are at 0 and 1. And many L functions are entire. They have no poles at all. Yeah, okay. And then, so it has meromorphic continuation and it satisfies the functional equation. So lambda of f 1 minus s is some number epsilon of f times lambda of f bar s. So under the functional equation, you have f and f bar are related. This number epsilon of f is equal to the root number of f, or root number of the L function. And it's a complex number with absolute value equal to 1. So if f equals f bar, we say that f is self-dual. And then in that case, then if you apply the functional equation twice in a row, this tells you that epsilon of f, if you square it, you get 1, and so epsilon of f has to be plus or minus 1. So so some of the L functions we'll be looking at are will be self-dual, and so that's going to simplify this root number. It's going to say it's plus or minus 1. Okay, so that's the setup and the notation, and then so now let's do some examples. And if there are questions, please feel free to stop and ask. Okay, so example. So the first example is always the Riemann zeta function. Which converges for a real part of s bigger than 1, and Euler proved that it has this Euler product. The gamma factor, so the f is sort of like the constant function 1. So I don't know, it's kind of silly to write it. So the gamma factor for the zeta function is just gamma r of s. The integer q is equal to 1. And so then the completed L function is just gamma r of s times zeta of s. And then this is equal to, or this is invariant under s goes to 1 minus s. And it has poles at s equals 0 and 1. So zeta has a pole at s equals 1 only. So the pole at s equals 0 comes from the gamma factor, but not from zeta. So once there's a pole at 1, because of the symmetry, it has to have a pole at 0. But then the gamma factor has a pole at 0. And yeah, and the zeta function is non-zero there. And yeah, so zeta itself does not have a pole there. Okay, so that's the zeta function. So this is a degree 1 L function. We see this in 2 ways. So from the Euler product is sort of a degree 1. So you have a single factor in the for each prime. This is a degree 1 reciprocal polynomial in terms of 1 over p to the s. And then also we have a single gamma factor. So I mean, I said, or I slipped this by, but we've got the gamma factor and the Euler product should have the same degree. So this is a hypothesis, an assumption in Ivanitz and Kowalski, and it always seems to be the case. But you know, there's some interest in looking at more general types of I guess definitions of L functions, and then seeing what can happen there. So, for example, there's the Selberg class of L functions, and that's a more general class of L functions than what I've presented here, although I think conjecturally they should be the same. But potentially there's more things in the Selberg class, and then there's active work in trying to narrow that class down and prove that it's maybe the same as Ivanitz and Kowalski, or maybe the same as the class of automorphic L functions. But okay, and let's just set that aside. So that's the zeta function. And then more generally, we have, let's take chi to be a primitive Dirichlet character, mod q. And I think I want to take q bigger than 1 here. If q is 1, then we just get the zeta function back. So we have the Dirichlet L function ls chi. So this is the sum from 1 to infinity. Chi of n over n to the s. And just like for the zeta function, basically the same proof that Euler gave for the Riemann zeta function proves that this has an Euler product of the same form, 1 minus chi of p over p to the s inverse. This is another degree 1 L function. There's a gamma factor associated to this. Let's call it gamma of s chi. So here it splits into 2 cases, so depending on the parity of the character. So it's gamma r of s if chi is even, which means that chi of -1 is +1, and then it's gamma r of s plus 1 if chi of -1 equals -1. So chi is odd. Okay, there's this integer q. Q of chi or whatever, Q of f. This is just Q, the same Q. It'd be bad to use Q for 2 different things. So so this is the Q. And then the completed L function is Q to the S over 2. It's the gamma of S chi, whichever one, depending on the parity, times the L function. And then this satisfies the functional equation that this is epsilon of chi, lambda 1 minus s chi bar, where epsilon of chi, we can say what it is in some sense. So it's the Gauss sum of chi over square root of q times 1 if chi is even, and it's times negative I, or 1 over I, if chi of -1 is -1. Okay, and then lambda of s chi is entire as well, so there's no poles. So yeah, so I'm not going to prove any of these facts about about the Dirichlet L functions, about the analytic continuation and everything, functional equation. If you haven't seen a proof, a good source is, well, you can find it in Ivanitz and Kowalski. There's also the book by Davenport. That's a classic. So that's the cast of examples for degree 1. Any questions so far? I'll drink some coffee. It's first thing in the morning here in New Jersey. Okay, so looks like no questions. So now let's talk about some degree 2 examples. So okay. So again, I can't really give all the details on this. I have to assume that you've seen some of these things before. I can't develop all this from scratch in the amount of time that I have. So let's start. So we're going to start with a modular form. So we have to. So that's a function from the upper half plane to the complex numbers. So let's assume that it's a holomorphic modular form, like a classical modular form. Of weight k, where k is an even integer. On the group gamma 0 of Q. So this is the set of matrices of the form A, B, C, D, such that all A, B, C, and D are integers. The determinant is 1, and that the lower left entry C is congruent to 0 mod Q. Okay, so yep, and so that's the okay, so that's our assumption that F is a modular form for this group, and so this means that F of AZ plus B over CZ plus D is equal to CZ plus D to the K times F of Z for all A, B, C, D in gamma 0 Q, and for all Z in the upper half plane. Okay, so that's a modular form. So so F of, so if you plug in like the matrix, so if you take the matrix 1, 1, 0, 1, that's always inside gamma 0 Q. And so this implies that F of Z plus 1 is F of Z. So F is periodic with period 1. So it has some Fourier expansion. So this means that F of Z we can write as a sum from 1 to infinity. Some coefficients that we'll call AF of N, E of NZ. Okay, so I'm sure you've seen this notation earlier today, but E of Z, I guess, E of something. E of Z is E to the 2 pi IZ. Okay, and I like to use the, I like to renormalize these coefficients. So I want to write them as lambda f of n times n to the k minus 1 over 2 E of nz. And okay, as an assumption, I want to assume that lambda f of 1 is equal to 1. So if lambda f of 1 is not 0, I can always rescale my modular form to ensure that lambda f of 1 is equal to 1. If lambda f of 1 is equal, or if AF of 1 is equal to 0, then I can't do this. But so I'm just going to assume my way out of the problem. So in all the cases that I care about, at least for these lectures, will have non-zero first Fourier coefficient. So there's a okay. So there's so the right. Okay. Also, I guess I forgot to say this word. So I want it to not just to be a modular form, but it's a Cuss form. So F of Z is a Cuss form. Okay, I think I'm not saying okay. I'm like not. So we also need to assume that we have a Fourier expansion around every cusp. So F has a Fourier expansion around any cusp. And we assume that the first sorry, AF of 0, so the 0 Fourier coefficient, the constant term in the Fourier expansion, I want to assume that that's equal to 0. And I want to assume this at each cusp. Okay, so that makes this be a cusp form. I mean, it's also interesting to study modular forms which are not cusp forms. All right, so we have, so we're going to let SK of Q equal so this is the vector space, complex vector space of weight K modular forms or cusp forms. So you get a vector space, and then this has a natural inner product structure. So this is the inner product is the Peterson inner product. By the way, if this is your first time seeing all this, I apologize. I mean, this is I'm sure you're lost. Like this would take weeks to really develop all this, like in a classroom setting. Like that, you know, this is um, this is too much. But if you have seen it, then this is just supposed to be a little review and a reminder, and I'm setting up the notation. So there's the Peterson inner product. So this is so if you have two modular forms, we can define their inner product, which will be an integral over the quotient gamma 0 q mod h, which you can think of as a fundamental domain for this group action. And so you integrate y to the k, f of z times g bar of z, and then we integrate dx dy over y squared. So this measure, this dx dy over y squared is invariant under the group. And so this is a well-defined integral. Okay, so that's our inner product. And then there's a collection of operators, these so-called Hecke operators. T sub n. So for each positive integer n, we have a Hecke operator T sub n, and it maps SKQ, I guess SKQ is my notation, to itself. And so the T sub n commute with each other. So this is a commuting family of operators, and these are self-adjoint with respect to the Peterson inner product for at least for the ends that are coprime to Q. Okay, and so that means that we can choose a basis of for SKQ consisting of eigenfunctions of all these Hecke operators. So simultaneous eigenfunctions of all the Hecke operators because they all commute with each other. Now in order to do this for L functions, I want to suppose that TNF is, I want to assume that it's an eigenfunction of all the Hecke operators. Okay, so this is a more special class of modular forms. Not every modular form will do this, but so this is for all n. So I know I can choose a basis of SKQ for integers coprime to Q, for the Hecke operators with indices that are coprime to Q, but I want to make a stronger assumption that we have a modular form that's an eigenfunction of all the Hecke operators. So this is possible. We have a nice basis of these eigenfunctions in a subspace of the full space of cusp forms. SKQ, so there's a nice subspace of SKQ, which is the orthogonal complement of the modular form, the cusp forms that you get that came from lower level. So that's sort of what's happening here. You have modular forms of lower level that you can think of as being in higher level. And so all the modular forms that you get from lower level, we think of those as old forms, and then they span some subspace of the full space of cusp forms, and then you take the orthogonal complement of that. And then that's the space spanned by the new forms, or that's the I don't know, the new space, and then there's a nice basis for that space. Anyway, we don't really need this. I just want to, I'm just mentioning this. So but we do want the nice cusp forms that are eigenfunctions of all the Heck operators. Okay, so we're not just talking about the empty set here. That's the point. Okay, so then now, yeah, right. So then I guess I didn't mention this verbally, but this lambda f of n, these are the same as our these are our normalized Fourier coefficients. So these Hecke eigenvalues, these eigenvalues for the Hecke operators are the same as the Fourier coefficients up to some scaling. Okay, and then great. So then now I can define the L function associated to a holomorphic modular form. You just sum from 1 to infinity, lambda f of n over n to the s. And then this has an infinite product over primes, 1 minus alpha 1 of p over p to the s inverse times 1 minus, let's say, alpha 2 of p over p to the s inverse. And I can tell you what alpha 1 and alpha 2 are. I guess up to permutation. They're only defined up to permutation. So the sum of them is lambda f of p, and then their product is so it's chi0 of p, where that's the trivial character mod q. So alpha 1 times alpha 2 is equal to 1 for the primes not dividing q, but for the primes dividing q, that means their product is 0. And so that says that like one of the alphas is equal to 0, and then the other one will just be your lambda f of p. Okay, so that's the Euler product. So this is a degree 2 Euler product, right? So we have in terms of as a function of 1 over p to the s, this reciprocal of this Euler factor is degree 2 in terms of this 1 over p to the s variable. So okay, there's a gamma factor associated to this. So this is just gamma c of s plus k minus 1 over 2, I think. Yeah, I think so. And then, right, which you can write in terms of gamma r's using the formula I mentioned earlier today. And then the q of f, this integer in the that appears in the completed L function is just the same as this q. So the same as the q in the gamma 0 of q. So then we form lambda of fs. So this is our q to the s over 2, our gamma of fs times our L function. And then this is equal to epsilon of f, lambda of f 1 minus s. And here f equals f bar. So this is for the L functions I wrote down, these are self-dual. The f equals f bar, and epsilon of f then is plus or minus 1. That's the root number. And I guess this completed L function is entire, so it has no poles. So, okay, so this is a family of degree 2 L functions that we can get this way. So a good reference for this would be Ivanitz's topics in classical automorphic forms. Okay, so just as a remark, we can study, we can generalize this to some extent. So we can study more or general or define more generally F's with a Nebentipus character, or also you could call it a central character. More generally, it's just a more general multiplier system. But this means that, so for example, it could mean that f of az plus b over cz plus d. So previously what I said was that this was cz plus d to the k times f of z, but more generally you might put in a character here. So you could say it's psi of d times what we had before, and psi is a character mod q, a Dirichlet character mod q. And then so the Nebentipus character is this psi. So you can look at modular forms that transform this way, and you can define Heck operators for these things, and a lot of what I said goes through, but it's no longer self-dual anymore. But anyway, this is I don't want to generalize everything to the maximum extent. I'm just trying to give some examples. So another, I guess, related family of examples will come from Maass forms. So these are, I don't know, I think more people know about modular forms than about Maass forms. So if you've seen modular forms but not Maass forms, then Maass forms are similar in a lot of ways and then different in one or two ways. So, okay, so we start again, or we look at, again, functions that are functions from the upper half plane to the complex numbers. Actually, for the setting I'm going to have, we could replace the domain with the real numbers instead. So you might think of these as real valued, but let's not worry too much about that. So there's an operator called the hyperbolic Laplacian. And so what is it? So it's negative y squared. So it's a differential operator. The Euclidean Laplacian would say you take the differentiate with respect to x twice, differentiate with respect to y twice, add those up, and maybe take a minus sign. And this is the same as that, except you multiply by y squared. So the Euclidean Laplacian commutes with Euclidean transformations. And here, this hyperbolic Laplacian commutes with Mobius transformations, which are isometries of the hyperbolic plane, the hyperbolic upper half plane. So, so this is a natural differential operator. It's similar to the Euclidean Laplacian, but in hyperbolic space. So then so a Maass form is just like a holomorphic form, except instead of being holomorphic, we're going to assume that it's an eigenfunction of the Laplacian. So a Maass form, and you can more generally look at more general weights, but let's just look at weight 0 Maass forms. So it's a smooth function from the upper half plane to the complex numbers. And again, I'll just write this there. We could replace the complex numbers with the reals. Okay, so it's going to satisfy these three properties. So f of az plus b over cz plus d is just f of z. So the weight is 0, so the cz plus d to the k, when k is 0, that's just 1, so I don't even have to write it. So this is true for all a, b, c, d, and our group, let's say gamma 0 of q again, and for all z in the upper half plane. So that's the kind of automorphy condition or the modularity type condition. It's just how it transforms under the group gamma 0 Q. So I replace the condition that F is holomorphic with a condition that you apply the Laplacian to F, you get a scalar times F. So F is an eigenfunction of the Laplacian. And here, this lambda is some complex number, although it's actually going to be real and non-negative. Okay, and then I want some kind of condition to say that it doesn't grow too fast at the cusps. So actually, I didn't even mention this when we were talking about holomorphic modular forms, but we put on some condition to say that as you approach each cusp, the function remains bounded. And then the condition of being a cusp form means it vanishes at each of the cusps. So here, all we need is some kind of weak condition, like that it's bounded by some small constant times. So it doesn't have too fast exponential growth. So if there's some, I guess maybe for each. So okay, you can get away with slightly different things here, but as long as it doesn't grow too fast, so if it doesn't have exponential growth at infinity, and we also need a similar condition at each of the cusps. So anytime you talk about how modular forms or Maass forms behave at different cusps, all you do is change variables to change your cusp to infinity and just expand your function around this other point. So it's best just to look at infinity and think all the other cusps are the same under a change of variables. So these are your three conditions that parallel the three conditions for modular form. Okay. So it turns out, so this number lambda infinity, it's natural to write it in this way as a half plus ITF times a half minus ITF, which is the same as a quarter plus TF squared. So it turns out that this eigenvalue is greater than or equal to 0. Okay, again, you can find a proof of this in Iwaniwicz's spectral methods and automorphic forms. It's not very hard. It's just an integration by parts argument. And so that implies that this T sub f is either a real number or it's either purely okay, I guess the way I wrote it is I already put in the I. So yeah, it's either what have I done? Okay. I guess the way I've defined it is either it's real or if I take the I times the TF, it's between minus a half and a half. Okay, so what, okay. I might have, some people would write ITF as the point for TF. And I sometimes, I might have changed it on the fly without really thinking about it, but it does, I guess it's just yeah. What I'm calling T sub f, many other people will call I times T sub f. And when I say many other people, that means often myself. So, but okay, so here T sub f is called the spectral parameter. And they come in these pairs, in these two symmetric pairs. And just like for holomorphic modular forms, we have Heck operators acting on the space of Maass forms. And so let's assume that f is an eigenfunction of these T sub n's. So the Heck operators, like that whole story is basically the same for Maass forms as it is for holomorphic modular forms. So if you're used to holomorphic modular forms, everything is the same. Like you don't really use anywhere that your function is holomorphic to define Heck operators. It's just a group theoretic property. So just like for holomorphic modular forms, Maass forms have a Fourier expansion, although the shape of it is going to be a little bit different. We're going to have a sum over integers. And okay, and just like before, let's assume f is a cusp form. So let's just say f vanishes at all cusps. So that means it's a cusp form. And then in the Fourier expansion, that means that the constant term vanishes. But now we have a sum over all integers, positive and negative. But the zero coefficient is gone. And so this is, I'll write it as lambda f of n over square root of absolute value of n times e of nx. And then there's some function w of ny. Here w is a Whittaker function. So what's going on basically is that when you, from the fact that f satisfies this differential equation, that it's an eigenfunction of the Laplacian, when you write down the Fourier expansion, you'll have some function of y, and then you apply the Laplacian to both sides, to both sides of this formula, and then that's going to imply that that this function of y satisfies a second order ODE. And the second order ODE that it satisfies is this Whittaker differential equation. So it has to be a Whittaker function. And I won't write any of this down, but yeah, it's a second order differential equation. So in general, if you have a second order differential equation, you'll have two linearly independent solutions. One of the solutions has exponential growth and the other one has exponential decay. And so the condition that we put in that says that our function doesn't blow up too fast at infinity is going to rule out the exponential growth solution to the differential equation. And then we get like the exponentially decaying one instead. So yeah, so anyways, this w of y, in fact, is related to a Bessel function. So it's square root of y, and then it's the k-Bessel function with parameter ITF, and then it's at 2 pi y. Okay, and then like I said, Tn, we're also just notation-wise, we use the same notation as we did for holomorphic modular forms. And so Tnf is lambda fnf. So those are the lambdas are the eigenvalues of the Heck operators. Okay, great. So now I can write down the L function associated to one of these Maass forms. So oh, maybe, yeah, okay, well, I forgot one last thing. So there's also a parity that sometimes people call T sub minus 1 of F. So there's this extra symmetry. It's not one of the classic T sub n's, like one of the normal or usual Heck operators, but it's a simple operator. It just sends f of x plus iy to f of minus x plus iy. So it's just like reflection over the y-axis. And right, and so this is an involution, and this t negative 1 turns out it commutes with all the other T sub n's, and we can assume that t minus 1 f is plus or minus f. The L function only uses the positive Fourier coefficients. Okay, it says my internet connection is unstable. I'm going to try to, well, I'm just going to proceed and hope for the best. So L of fs is the sum from 1 to infinity, lambda f of n over n to the s. So we only have the positive ones. This has an Euler product, 1 minus alpha 1 of P over P to the S inverse. It looks exactly like the case of holomorphic modular forms. There's a gamma factor. So the gamma factor is what looks different. So the gamma factor is gamma R of S plus ITF times gamma R of S minus ITF for F even. And if F is odd, it's just like for Dirichlet L functions, you get this extra shift by 1 in the gamma factors. Okay, so that's the gamma factor there. And then we have the completed L function. So this is Q to the S over 2, gamma factor gamma of Fs times L of Fs. And then this will be our epsilon of F times lambda of F 1 minus F. And your epsilon of F is, again, so this is the root number. Okay, so and it's entire. So we get an entire function, no poles, and it satisfies this functional equation. So these are the two types of degree 2L functions that we'll want to be working with in my some of my forthcoming lectures. Okay. Real briefly, I've got a couple, I've got a degree 3 example and then some degree 4 examples. So for degree 3, so take F to be either holomorphic or Maass form. So holomorphic modular form or a Maass form as before, just in what we were talking about in the degree 2 case. And then there's what's called the symmetric square L function. So you take, so the symmetric square L function, I can tell you what the Dirichlet series is. So it's a sum over M, sum over N, lambda F of N squared over M squared N to the S. Okay, I guess I have to cheat slightly. So I'll just write this equals with the dot sign on it. So, okay. So if I compute this right-hand side, this will have an Euler product of degree 3. So this is the product I equals 1 to 3, 1 minus alpha I of P over P to the S inverse. Right, and so there's a little bit of an issue at how we define this for the primes dividing Q. Okay, so primes dividing Q are a bit tricky. So this even comes up for Dirichlet functions. So if you take a Dirichlet function, or if you take a Dirichlet character that's not primitive and you write down the L function associated to it, that might not, if the character is not primitive, then the L function that you write down doesn't satisfy the right functional equation. You've got, like, some of the Euler factors are off. They need to be corrected. And it's a similar thing here. It was the same thing actually with the modular forms and the Maass forms. I was secretly assuming, if you go back, I remember I said there's like this nice space where this thing is an eigenfunction of all the Heck operators, where we can get these eigenfunctions of all the Heck operators. And yeah, and so that's this space of new forms that where we have this nice property. And so anyway, so there's always kind of a tricky, a bit of a tricky business to sort out exactly what happens for maybe finitely many primes that divide like the level that's under consideration. So okay, but let's not worry too much about it. I don't think we need the exact shape of the Euler product. So all but finitely many primes in this Euler product are as I wrote them. So okay. So there's a gamma factor associated to this L function. So actually, I mean, if you want to just take Q equals 1, just take level 1, and then what I said is then there's no primes dividing Q, and everything is perfect. So you don't have to worry about it. So the gamma factor will be, so it depends on if it's a Maass form or a holomorphic form. So if it's a Maass form, it's gamma R of S plus 2 ITF times gamma R of S times gamma R of S minus 2 ITF. For F Maass form. And then for a holomorphic form, I think it's gamma R of S plus 1 times gamma C S plus K minus 1. But okay, anything I write here you shouldn't trust without, don't if you're writing a paper or something, don't rely on my formulas that I hopefully transcribed correctly from other sources, but look up the real references for this. But anyway, so so here the gamma factors, we also have 3 gamma factors. That's consistent with this being a degree 3 L function. So the gamma C, you might say, oh, that's just 1, but remember it factors as a product of 2 gamma R's. So this is degree 3. We have 3 gamma R's, so it is degree 3. So okay, the conductor. So the Q. So the Q of some, okay, I just, yeah, so this thing we'll call capital Q. It's, again, I think it's a little bit tricky to completely pin it down, but it's Q squared at least if Q is equal to a prime. And epsilon of F is plus 1. So I believe it's tricky to pin down the conductor in general. But yeah, anyway. So, okay, so these are these symmetric square L functions. They're basically like the L function that you get by sampling your original L function, but only on squares. So, so in this Euler product, this is, the coefficient of 1 over p to the s is lambda f of p squared. And then there's higher order terms that come in. Function. Okay, so that's symmetric square, and then for degree 4, so this will be our last examples. So these are Rankin-Selberg functions. So okay, so let's say F and G are Maass forms. You can do this for holomorphic forms as well. And I think let's assume that they're both even. So I think the main thing is I think I want them to have the same parity. And let's say F has level Q1 and G has level Q2. So the L function associated to the Rankin-Selberg convolution. So we write this like formal tensor symbol, F tensor G. It's just a symbol here. And again, I'm going to write this dot here because the precise definition is a little bit trickier to write down. So it's lambda f of n times lambda g of n over, oh, I forgot, I think, yeah, I think we still have this m squared n to the s, right? I think that's still there. And so this has an Euler product over primes, and it should be, so it's like a product from I equals 1 to 2, product j equals 1 to 2, 1 minus alpha I. So f has these parameters, and so does g. So let's write the ones for f as alpha I comma f of p. And then we have alpha j comma g of p over p to the s inverse. So you take, so alphas are the local parameters, like those are the things that appear in the Euler product for the L function associated to f and g respectively. You just multiply those together in all possible ways. So you have two for f, 2 for g. You take all their products, so you have 4 different things. So this is a degree 4. And this is, again, it's just not quite right, or it needs some patching up for the primes dividing Q1 and Q2 potentially. So this is okay for P not dividing Q1, Q2, needs quote unquote fixing for P dividing Q1, Q2. Okay, so that's the L function. There's a gamma factor associated to this. So this is the product. So again, we've got like a double product. So it's gamma R of S plus, oh, let's say epsilon ITF plus epsilon J ITF. Where epsilon I and epsilon J are just are in that set. I don't know. I guess you could say epsilon 1 is 1 and epsilon 2 is -1. So anyway, you're just taking all possible sign combinations of plus or minus ITF plus or minus ITG. And those are your gamma factors. So you get 4 gamma factors. Q of F times G is a bit tricky. So I can't just say what it is. It's not like it's just Q1 squared, Q2 squared, or something like that, although in many cases it is. So if, for example, GCD of Q1 and Q2 is equal to 1, then I believe that this conductor will be, or this integer, I didn't even call it the conductor, but this integer is Q1 squared times Q2 squared. I believe that if Q1 equals Q2 is equal to a prime, the same prime, then Q of F times G, I think, is P squared. But for example, if they're both P squared, then the best I can say without any other hypotheses or extra information about F and G is that it's somewhere in this, it could be 1, it could be P squared, or it could be P to the 4th. It could be any of these 3 possibilities. And there's a nice paper by Winnie Lee. I want to say from around 1980. I think it's just called L series of Rankine type and their functional equations, something like that. And anyway, she writes all this down. I mean, it's the note, it's like pages long just to sort of figure out what all the notation means and see what's going on. But like she'll tell you exactly what it is, but you have to go through this process to get there. And so it's pretty complicated to write down what all the L function data exactly is. And she tells you also what this correction factor is for the Euler product. So she writes down, like, you might call this the naive, this thing I would probably call this the naive L function. It's sort of like, actually you might want M coprime to Q. So I think that's what she would call the naive L function, or that's what she would write down and call the L function, but it's not really the right L function. It's not the not the true L function in the the Ibanez and Kowalski sense. And she will say exactly how you need to modify the Euler factors to get the right L function that satisfies the right functional equation. But once you do this, then you've got this number. So then we've got our gamma. So then we've got all the data. So the completed L function will be this Q. What did I call it? I call it little q, just whatever it is. So Q of F times G to the S over 2, gamma of F times G S times the L function. And then this is equal to some root number, lambda F times G 1 minus S. So maybe it might be that under the hypotheses I have so far, the root number is always +1. But yeah, she works everything out. Like F and G could have Nebentibus characters. They don't, so she allows all these sorts of more general things. And then in that case, this root number may not be plus or minus 1 anymore. But anyway, you get these degree 4 L functions. These are extremely useful in various ways. Anyway, so this concludes my list of examples of L functions. Some of degree 1, some of degree 2, some of degree 3, and some of degree 4. Okay. So, right. So let's define one thing. Again, please, feel free to ask questions. So I want to define the analytic conductor. Maybe you saw this earlier. I don't know. I was asleep when other things were happening. So yeah, it might be good if I knew what was being covered in all the other lectures so far. But okay. Anyway, let's just move on. So let's let L of Fs be an L function. So it's got its sort of arithmetic conductor Q, that's this positive integer. We've got our gamma factor. Okay, so it's got those two things. Then I want to define, so this is, again, I'm just following Ibanez and Kowalski here. So define Q infinity of S to be the product from 1 to D. So absolute value of S plus the kappa J plus 3, something like that. The plus 3 is maybe not so important. Maybe they just chose an integer bigger than E. Okay, so this is some quantity. It takes into account the size of the gamma, at least the size of the arguments of those gamma factors. And then there's a total analytic conductor, which is called Q of Fs. So Q is sort of overloaded here, but that's how it is. So it's the regular Q of F. That's the integer, and then you multiply by Q infinity of S, and this is called the analytic conductor. So for example, for zeta, so if you have zeta of a half plus IT, this has analytic conductor. I guess technically it's 3 plus the absolute value of t. I'll just put quotes. We would just call this t. In the business, we would just call it t, not 3 plus t. But so the three is just to say like, okay, if t is small, like 0, we don't want the conductor to go to 0. So adding some constant to it prevents that from happening. So the analytic conductor of the zeta function in the t aspect is just like t. The analytic conductor of L of a half chi, this just has conductor q. If you allow for both t and chi to vary, this will be q times 3 plus t. So you can have like these hybrid things. So you can have t and q varying in some way. If f, or I guess if L of fs has degree d, and the kappa 1 up through kappa d are just fixed, you just think of them as like just fixed numbers, then the q infinity of s should grow like t to the d. So sometimes we study questions where we might be looking at like holomorphic modular forms of large weight. But so the kappas or these numbers might be changing. But other questions, we keep them fixed. And so if we keep them fixed and we look in the t aspect, then it grows like t to the d. So I guess an example where they would vary, like the gamma factors might vary in a different way would be like f is a weight k modular form. Then, so the gamma factor, whoops. So the gamma factor was, I think, gamma c of s plus k minus 1 over 2. And so this would be gamma r s plus k minus 1 over 2 times gamma r, s plus, the same thing, but plus 1. So I guess it's k plus 1 over 2. So our q infinity, let's say of a half. So if we just study them at the central point at s equals a half, this should be like, okay, let's just plug in the definition according to Ergodic and Kowalski. This would just be so a half plus k minus 1 over 2 plus 3 times a half plus k plus 1 over 2 plus 3. But anyway, this grows like k squared. So the analytic conductor, or at least the sort of the infinity part of it, the gamma factor aspect of it, grows like k squared for holomorphic modular forms. And similarly, so if you take a Maass form, where, so there we had gamma r of s plus ITF, gamma r s minus ITF. That's our gamma factor. So then our q infinity of this thing at a half would be like, it would grow like t sub f squared. So it's like the square of this spectral parameter. But there's other funny things that you can do too. So you can look so there's like more generally, it's let's say we look at a half plus I don't know, a half plus iy. This would be like y plus t sub f plus 3 times y minus t sub f plus 3. So and then this thing can do all sorts of funny things depending on how close y is to t sub f or not. So for example, q infinity of a half plus I t sub f because one of the have a well-defined meaning, but I think yeah. So typically it's like t sub f squared, but then at certain values the conductor drops down, and so now it's only like degree 1 in terms of t sub f. So it's almost like a degree 1 L function in terms of the size of the conductor. Okay. So that's the notion of the analytic conductor. It's a extremely important invariant associated to an L function. And so it'll come up in the quite a bit. So next I want to talk about the approximate functional equation. So the approximate functional equation is a way to get kind of an essentially finite formula for an L function inside the critical strip. So inside the region between real part between 0 and 1, where the Dirichlet series does not converge absolutely. But nevertheless, we can get a useful formula inside this region. So just to say a little bit about like the notate, like the terminology, it looks really funny, but here's an old-fashioned approximate functional equation for zeta. I guess I'll call it old-fashioned. Hopefully that's not derogatory. So for this, you can see Titchmarsh's book, Theorem 4.13. I'm just grabbing this from Titchmarsh. So let's take S of sigma plus IT. Sigma is between 0 and 1. And then let's take T positive. So what he does is say, okay, let's take two integers, or actually real numbers, positive real numbers, x and y, such that 2 pi xy is equal to t. And he says, so I think he wants x and y bounded from below. So it's not like one of them is going to 0 and the other is going off to infinity. He's assuming that they're both bounded from below. Then, okay, then the conclusion is that zeta of S, which is our zeta of sigma plus IT, is, we can write it as two finite sums. So we have a sum n up to x, 1 over n to the s, and then we have a sum n up to y. Oops, I didn't leave space. So plus chi of s. I'll say what chi of s is. Some 1 over n, some n up to y, 1 over n to the 1 minus s. And then there's an error term. Okay, and so chi of s, let me say what everything is. So chi of s is, I guess we can implicitly define chi of s via, so zeta of s satisfies an asymmetric functional equation. So zeta of s is chi of s times zeta of 1 minus s. So the way I wrote the functional equation was that the completed L function is invariant under s goes to 1 minus s. What you can do is just solve for zeta of s, and then you'll have zeta of 1 minus s on the other side, but then you'll have some ratio of gamma factors, and just call that chi. That's what chi is. Okay, and then so that's chi, and then the error. Why is this not working? Error. So the error term is big O of x to the minus sigma times log of t, and then plus another error term of size t to the half minus sigma, y to the sigma minus 1. So often what you might choose is x and y to be the square root of t. So that's like the most balanced form of this. So at x equals y equals square root of t over 2 pi. The error is t to the minus sigma over 2. I think. Okay, and sigma is a quarter, so or let's take and at sigma equals a half, then it should be t to the minus a quarter times, let's say, log of t. Is this right? Yeah, when sigma is a half, yeah, that's right. So the error, so this is something that goes to 0 as t goes off to infinity. So this lets you approximate the zeta function inside the critical strip by these two sums that you chop off at x and y respectively with some reasonable error term. Okay, so this is like the old-fashioned approximate functional equation. It's an actual approximation. You have a main term and you have an error term. You have two finite sums. One has x terms and the other has y terms. So this is all well and good. There's nothing wrong with that. But when you try to generalize this to more general types of L functions, the proof of like the estimates of the error terms start to break down, and it becomes problematic. And so there's a maybe better form of this for at least for generalizations. So the more modern form of the approximate functional equation, I mean, this took a long time to, I mean, I call quote unquote modern version of the approximate functional equation took some time to settle on. So for this is the most common reference for this is theorem 5.3 of Ivanyi and Kowalski. So I'm just going to state the theorem from their book. So let's let L of Fs be an L function. Let's let G of U be a holomorphic function. Bounded, let's say, in vertical strips. G of minus U will be equal to G of U, so it's an even function. And let's normalize it so that G of 0 is equal to 1. Okay, so that's this. You have this complex analytic function that appears inside here. X is going to be a positive parameter. And then for sigma between 0 and 1, we have a formula for our L function. So this generalizes the previous approximate functional equation as follows. So we have a sum from 1 to infinity, lambda f of n over n to the s. So instead of chopping it off at x, I'm going to I'm not chopping it off anywhere, but I'm putting on a smooth weight function. And it's v sub s of n over x times square root of q. And I'll say what all these things are. It takes a little while to write everything down. There's a second term. You have this epsilon factor. That's the analog of chi, the chi of s from the approximate functional equation for zeta. So we have this kind of thing. So now we've got our epsilon, we've got the coefficients conjugated, evaluated at n to the 1 minus s. I have this v function. And then there's a minus a term r. And I'll say what all these things are. Okay, so v sub s of y is 1 over 2 pi I integral over a vertical line, let's say over the line 3. So it's y to the minus u, g of u, gamma of f, s plus u, over gamma of fs du over u. Epsilon of fs is epsilon of f. That's like epsilon of f is just the root number, but this is like, we have two components of it here. So we have a q to the half minus s, and then we have gamma of f bar 1 minus s over gamma of fs. Here R is often, most of the cases we care about is 0. I don't think I've ever had a paper where I had to actually write down what R was. I always made it, there's always 0, but okay, but it's the residue at u equals 1 minus s plus also the residue at u equals must just be negative s. Sum up the two residues of the following function. So it's the completed L function at s plus u over okay, q to the s over 2 gamma of fs. That's just, it doesn't really matter. It's just a normalizing thing. G of u over u, capital X to the u. So in particular, this is equal to 0 if lambda of fs is entire. Okay, but for example, if you wanted to do this for the Riemann zeta function, you'd get this residue term. So R is just this residue term that sometimes comes up. And so this is the formula. This is okay, I'm not gonna have time to prove this today. Maybe we'll start with proving it next time. But let's at least observe why we should think of this as a nice generalization of the classic or the old-fashioned approximate functional equation. So structurally, it's similar. We have two sums. We've got this epsilon factor. So this epsilon factor, this is like the generalization of chi. So this is the thing that's going to come up when you write down the asymmetric form of the approximate functional equation. Maybe I can write that. That's something I can do in just a couple minutes. So I can write that down, and we can see why that's the same thing. This v sub s function. So if we had the Riemann zeta function, the q would equal 1. We'd have v sub s of n over x and be 1 minus s n times x. So it turns out that v will have decay once you're this n over x root q, this thing you're plugging into v, once it's bigger than the conductor. So there's rapid decay once you're past the conductor. And so that's kind of the part that tells you that like the two sums, if you chop one off at x, the other will be like at the conductor over x. And that's like, that was this relation that like the product of x and y was going to be the conductor. T is the conductor here, up to this extra 2 pi business. Okay, so it'll have that overall shape, but I mean, in a lot of ways, this is better than the previous form, because this v function is actually like a really nice smooth function. Whereas here in the classical one, you have this like discontinuous cutoff function. So it's like you're multiplying by the function that's 1 up to x, and then it's 0. So it's like a cutoff function that's not even continuous, not to mention smooth, or differentiable. So so this v sub s function is nicer for a lot of for analysis than the other one. The downside is that it's like a little bit more difficult to see like how this thing behaves. It's like the definition is certainly more involved, but in actual fact, it's not bad at all once you get used to it. So just to I guess I'll just okay. So something I can do in 1 minute is observe why this epsilon of f is like the chi of s. So remember, we've got our lambda of fs. That's our q to the s over 2. Gamma of fs, L of fs. And then this is equal to the root number. And then the same thing at q to the 1 minus s over 2. Gamma of f bar 1 minus s, L of f bar 1 minus s. And so which one do I want to solve for? So this says L of Fs is equal to epsilon of F. So Q to the 1 minus S over 2 over Q to the S over 2, gamma F bar 1 minus S over gamma of Fs, L of F bar 1 minus S. So this whole thing in front, that's epsilon of Fs. If I did this right. Let's see if can I zoom out a little bit here. So you see it's the same. So this is like the analog of chi of S. So this is like the right factor to come in, that comes in when you look at the asymmetric form of the functional equation for your L function. So yeah, I'm out of time. I know, I'm sure it's been a long day down there, and so why don't I stop here? So next time I'll start by proving this approximate functional equation, and then we'll start. We'll actually prove something about some moments. I'll try to talk about applications, and I guess you'll just have to wait and see what's in store. But I'll stop here. Yeah, thanks for your attention.
Thank you for the nice talk. Are there any questions?
There in the integral, well, when you define bs of y, is there any reason why you take the integral around 3? No, down there.
Oh, where did it go?
Oh, yeah. Yeah, here. Why is it the integral with real part 3?
So it's just something far enough to the right that that everything, like that I haven't hit any of the poles of the gamma factors.
Okay.
So it'll come up in the proofs, like that's where it comes up. But so by Cauchy's theorem, you can shift the contour around as long as you don't hit poles. And then if you hit poles, then you have to pick up residue terms.
Okay, but so could it be okay to take anything that had real part greater than 1? Or do we have
yeah, it should be okay. I guess the only thing you have to worry about is in the gamma factors. Okay, I slid this under the rug, but now it's coming up. So the gamma factor. So what we have is gamma f of s plus u, and then this is going to involve your gamma r of s plus u plus the kappa. So this is product over I. And I haven't said anything about the kappas. But if they were like, if one of them was negative 100, then we'd be in trouble. And so the kappas they're conjecture. So it's a conjecture that the real part of all these kappas is greater than or equal to 0. But I think what we know is something more like real part of the kappas is bigger than, I mean, maybe something like -1 is maybe, I think, something we might be able to prove, or maybe it's just in the way Bennis and Kowalski do it. I think this is the hypothesis that is basically all examples we know will get this. So so u equals 1 might be okay for that, as long as s is between 0 and 1. So that might be okay. That might be right on the line of where it's okay. But I didn't, yeah, but for this integral, it doesn't really matter. I just want it sufficiently far to the right that I'm not hitting any pole.
Okay, it does not look like there are further questions. Then let's thank the speaker again very much. Okay, thank you.